ॐ श्री गुरुभ्यो नमः। हरि ओम्। ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः। ॐ असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतं गमय। ॐ शान्ति शान्ति शान्तिः। ॐ सर्वेषां स्वस्तिर्भवतु सर्वेषां शान्तिर्भवतु सर्वेषां पूर्णं भवतु सर्वेषां मङ्गलं भवतु। ॐ शान्ति शान्ति शान्तिः। ॐ लोकाः समस्ताः सुखिनो भवन्तु लोकाः समस्ताः सुखिनो भवन्तु लोकाः समस्ताः सुखिनो भवन्तु। ॐ शान्ति शान्ति शान्तिः। ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते। ॐ शान्ति शान्ति शान्तिः। ॐ श्रीगुरुभ्यो नमः। हरि ओम्।
Thank you. Please pray to your parents for a minute. I'll wait. Thank you. So, group 6, Yuvraj, are you ready?
Yes, sir.
Yeah, we can start.
So this is Yuvraj from Group 6. I'm here to present our work towards the wing design for the amphibious aircraft. And so in the next slide. So first step towards this is selection of airfoil, and to find that we have to calculate the design lift coefficient range. So the design lift coefficient range for the wing was found to be 0.4 0.453 and 0.458, and
How do you
average design
find this? How do you find this, Yuvraj?
using the formula that's mentioned there, sir.
What is the formula? What is the way?
What is the coefficient lift during the cruise formula, where it's equal to Q, the dynamic pressure times.
Okay. That's all.
Yeah.
Can you explain a little bit more?
So we take the lift equal to weight.
Okay.
So that's how the formula is.
That is right. But how do you find the range? You found, between 0.453, 0.45, you get those numbers. Yeah.
Yes, sir. So we'll be having we use the this wing load estimation. So in that we had the data, a range of data. So using that we get this.
Wing loading, where do you get that data? Wing loading is just a single number.
No, sir.
Wing loading is just one number, no? Where do you get the data from?
Yes, sir.
Do you get two numbers from there?
From the start of the cruise and the end of the cruise.
Wing loading, you found only one wing loading you got.
Okay. So we'll use
Continue. Yes, continue.
Okay.
Get it cleared from your teammates or myself later. Okay.
Okay, sir.
You can ask me. if you still don't.
Okay.
Yeah.
So and then we find the range for the design CL for the wing section that we got as from 0.503 to 0.508, and then the average design CL for the airfoil is 0.506.
Okay.
So using this design CL, we took 4 airfoil to compare, of which the NACA 4415 found to be optimal. So you can see in the next slide that we have the few graphs with the provided airfoil data. So in the next slide, we started with 3D.
The Mach number is 0.42, is it? Your Mach number is 0.42, the flight Mach number. What is it?
It's not. It's around 0.25.
0.25. Okay. Then actually you can go for a thicker airfoil, even though performance is not good. What is the thickness of the airfoil you have chosen?
It's around 0.05. Sorry, yeah, 15%, sir.
Huh? Again?
15%.
15%. That is, you have chosen this NACA 4415, is it?
4415. Yes, sir.
Yeah. Okay. Good. Good. Okay. No problem. You've done the right thing. Yeah. Good. Great.
So then we started with the 3D lift coefficient estimation. In that, we first found the slope dCl by d alpha to be 5.08 per radian, and then we took the values for.
Instead of 2 pi, what did you substitute? The formula. Did you substitute something else for 2 pi? 2 pi? Or just took it as 2 pi? Instead of 2 pi, you should substitute the 2D slope of the airfoil. Lift curve slope of the airfoil. Okay. So don't use the formula as it is.
Okay.
Just make a small change. So everything else will change
Okay.
after that. Anyway, continue.
Okay.
Hmm.
So from the CL versus alpha plot, we got the alpha not L value as 0.0 minus 0.075, right? And using this, we got the CL at alpha equal to 0. And using that, we found the CL value to be 0.455, which is actually not considered, but the value is 0.455. So in the next, we can see a graph with the plots of 3D lift curve, theoretical 2D lift curve, and experimental 2D lift curve. Here we use the equations for the 3D lift curve and theoretical 2D lift curve. So it's linear, and experimental 2D lift curve, we have used the airfoil data, so it's different. And on the right, we have the track record.
What is it? Experiment airfoil data you told. What is it? Airfoil data?
For the NACA 4415.
Where did you get the data from? Where is the reference? 2 you have given. Okay, no problem. Yeah. Later you
X4
tell
is
me X-foil. Which one is curved X-foil?
So actually, we use the data from the airfoil exploration.
No. See, you have 3 curves here. 3 lift curve.
The green
Theoretical
one,
2D lift
the
curve.
experimental one.
Experimental one, how do you use X-foil there?
So the data from the
right side, right hand side?
yes, sir. So the right hand side, using the about and Dohanov book.
Then what is the green
the
line? Green line is that data. You don't see a kink there.
Which one, sir?
See, in that CL alpha curve,
Yes, sir.
the green line has a small kink or something, keeps increasing around 5 degrees, 5 to 7 degrees.
Yes.
Huh? There's a sudden dip, sudden increase, then sudden decrease. It is non-linear there, correct?
Yes, sir.
I don't see any such non-linearity in the curve you're showing on the right hand side. Where is it?
Yes, sir.
Are you plotting the right thing?
Yes, sir. Actually, for the other two, we use the equations, and here we use the data, experimental data.
Value there may be something.
And as it is an
Why
X-foil, we actually got the CLS alpha values from the X-foil only, sir.
Which
for
is
that experimental.
green or red? Green or red? Which one?
Green in the left side, bottom one, green.
So green X-foil means not experimental. X-foil is just a tool. It's not an experimental one.
Yes, sir.
The experimental one is a red one, right side. What you have?
Okay, sir.
Okay. What you have immediately on the right hand side. Section is called CL, bottom alpha. That is
So
experimental.
actually, yeah, this is just a small simple plot, but on the right side we have the experimental plot. I mean the data.
So that you compare your 3D lift curve with that curve. That's all. Nothing else is needed.
Okay.
Yeah. On the right hand side, you plot it on the graph. Same graph you plot the 3D lift curve also and compare.
Okay. So
For the highest possible Reynolds number. For the highest possible Reynolds number, right? 6 into 10 power 6. There is something on the top. What is that curve for? The topmost one. See on the right hand side.
The CLS is alpha.
Yeah. What is the topmost one? What Reynolds number? Triangle. What is the triangle?
You mean the peak you're asking, sir?
No. See, there are 5 curves on the right hand side. Right?
Yes, sir.
For the CL versus alpha. 4 are very close together. But the 5th one is separate from the others.
Totally. Yeah.
What is that separate one?
It's another Reynolds number which is 9 into 10 power 6 or something in the closer to that.
I need to see all those numbers there. Okay.
Okay, sir.
I need to know which.
So the red one is our Reynolds number, and others are comparison. So we forgot to add it. We'll add it in the report there.
You also tell the page number on which it is. There is 2 in your reference book. PP. PP means page number. The page number in which you can find this graph.
Yes, sir.
Okay. Yeah. Okay, continue.
Yeah, from the graphs on the right, we get the stall characteristics. Moving on to the next slide, we have the taper ratio and sweep angle. So from the cookbook, which says that the ideal taper ratio value is 0.4 from the
Okay,
historical
go to the
data.
next. Yeah, go to the good.
And
Go to the next slide.
so in the drag estimation, so we use this formula. In this, the third term is neglected because the design CL range falls under the drag bucket. And from the book, we took the value which recommended the value for the Oswald efficiency E is equal to 0.8. We found the K value. And in the CD not estimation, in the next slide, there for the foam, we use this formula to get 1.39 as value. And for the interference factor, we use the high wing mid wing so that we can reduce the contact between the water and the wing as much as possible. Totally avoided. And the wet plant foam, we use this formula, and with the airfoil data of T by C max, we got 173.394 meters square. And as this is a turbulent flow, with this CF formula, we got one.
Okay, got it. Good. Next one. No, it's okay. You're doing correct. Yeah.
So with this CD, with this we found the CD naught value and substituted for the CD estimation. With all the values that we had, we got 0.017, and therefore got the L by D as 26.4.
Okay, good. Next
and
one.
at last, we have some physical dimensions that we calculated. The planform to be 426, the aspect ratio to be 8.4, and the wingspan 26.7. So it's mentioned there in the PPT.
And what is the wing drag in Newton?
Wing drag in Newton. Actually, we didn't do that, sir.
So how do you think you can, if I say I have this wing flying, I want its drag in Newton now. How many newtons drag is coming on this wing when it's flying, it's cruising at design point? How will you find it out from the what you have done already?
We can use the drag equation. With the,
yeah. What is the drag equation? Tell me.
0.5 rho v half rho v square.
Then?
Into S. Yes.
Into?
Planform.
No, that is it. Half rho v square S into?
Sorry. Into CD, sir.
How will you find that CD?
Sir, we found it now, sir.
Where do you find it?
Just now we estimated now, sir, in the last PPT before the.
Correct.
So, yeah, we get
CD naught plus KCL square. So correct.
Yeah.
Okay. Okay, good. So any questions to Yuvraj? Huh? Yuvraj, you find out clearly, how that CL range is coming.
Yes, sir. Okay, sir.
It's very important to know that.
Sure.
Any questions to Yuvraj? If no, we can go to the next presentation. Thank you, Yuvraj.
Thank you, sir.
Thank you.
Excuse me, sir.
Yeah, who's that?
Sir, I am Ananta Krishnan.
And tell me, Anthony.
Yes, sir. I have one doubt, sir. Like we tried our analysis of our for learning, we tried our analysis of our airfoil and X-foil. In that, I gave angle of attack from different range, sir, from -10 till 20.
Okay.
But the values were not like there was no situation where we didn't have a value that didn't converge. So every value is converge, sir. So
Yeah. See, X-foil is actually, why is it working fast? Why didn't you use a CFT? Each run will take a few minutes to run. In X-foil will be over in a few seconds, correct?
Yes, sir.
So it is because X-foil use an approximate form of Navier-Stokes equation. It is called, parabolized Navier-Stokes equation, PNS, which can be solved analytically, and it can be solved just like a Euler method using panel method you can use to solve it. That is inside the boundary layer. Outside the boundary layer, it is using Euler equation. Now it is matching these two. So it is not solving the exact equation. It is solving an approximate form of equation to give you an estimate. So surprisingly, just by luck, it agrees sometimes better with experiments than with than CFD results. CFD results even better than CFD results sometimes. We don't know why. It should not, because it's more approximate, right? But it does. But beyond stall, it gives crazy results. You can't trust it beyond stall. It may give some result. It may converge, but you can't trust the result.
Yes, sir.
Okay. Yeah. Because you are solving a different set of equations. The parabolized Navier-Stokes equations are not valid for stalled flow or separated flow. So they use some approximation whenever there is separation bubble or something. They don't consider such bubbles in their analysis.
Oh, okay, sir.
That is why it may converge, it may give you some results. It's not correct. That's all.
Yes, sir.
So the problem is stall angle. It may over predict your stall angle because of this.
Yes, sir. We were able to like look for that because even if we had a higher angle of attack, we had the lift coefficient and the drag value.
Correct. That is because of the governing equation they use are different. They don't give a correct representation of the actual flow field at high angle of attack. That is the reason. Okay, good question.
Thank you, sir.
Thank you. I should thank you because these good questions will actually enrich the knowledge of the class if somebody is listening. Okay, so thanks, Anand. Yeah. Now Rajshri has a question.
Sir, just a small question that in continuation to what you said before.
Wait. Let's finish the next one, then we'll continue. Remind me. Huh? Yes. Remind me after the next presentation, we'll continue.
Okay.
So we'll go to the next presentation.
Hello, sir. Sir, I'm Nandakumar. Sir, Nandakumar, sir.
Nandakumar, roll number?
57.
Okay. Continue, Nandakumar.
Yes, sir. Hello, everyone. I'm Nandakumar. I'll be presenting on behalf of my team, and my teammates are Sibi, Pawan, and Srivasan. This is the design specification given to us. The black and one is what sir gave to us. That's all we chose. And this is our mission.
Show me again.
Yes, sir.
Wait. Did I specify that it should be a turbojet engine?
Sir, no, sir. Actually,
okay. You found out. Okay.
Sir, yes, sir. The black and one is what you specified, sir. Others all we just now we have chose, sir. During engine design, we'll choose better.
Yeah. Mark number you chose based on?
Sir, mark number based on, sir, actually it was around 0.6 to 0.7, sir. Sir, but I wanted to check what will happen at 0.8 Mach number for our for military cargo aircrafts.
Military cargo, is it necessary 0.8?
Yeah. Yes,
The
sir.
reason
Okay.
is 0.8 means there will be more complications in the design. Transonic flow design is more complicated.
Yes, sir. So only we have used the supercritical airfoil, sir.
That is okay, but it will add to the cost of your design. Anyway, I mean,
yes,
I don't mind. You can play with it. I have not specified. So you
yes.
can design. You are free to do so. I'm just telling you what will happen.
Okay, okay, sir. Yes.
Yeah, yeah.
Sir, this is our primary mission profile, sir.
Hmm.
Then airfoil selection based on the calculations at cruise start and cruise end, we have got this value. We chose thickness to ratio part, and the airfoil family is supercritical airfoil. Wing area is 200 meters square. Then based on the drag bucket, we chose airfoil, which has a maximum thickness of 14% at 36% of the cord, and maximum camber 1.5% at 83% of the cord. Then
It told designed for 0.4 lift coefficient. Do you
sir,
mean the design? Do you mean design lift coefficient of this airfoil, or the lift coefficient for which you have designed the cruise design?
sir, design lift coefficient for this airfoil, sir. Sir, around
It's not.
0.43.
It is not really necessary to mention that or bother about this at this point of time.
Okay, sir. Okay, sir. Yes, sir.
Okay.
So leading edge sweep angle
Wait,
was.
wait.
Yes, sir.
What do you? How is the supercritical airfoil different from other types of airfoil?
Sir, it reduces the wave drag, sir.
How?
Sir.
In the
Yes, sir.
shape wise, how is it different? Shape wise. This was a gate question, so I'm asking you now.
Shape wise, sir.
How is it different from other airfoil? Shape wise.
Maximum camber it will go like reflex airfoil. The lower coordinates will go above, sir.
That's all.
Sir, then
This was a gate question earlier, multiple choice. Okay. The correct answer to that question is a rounded leading edge. Okay. And
yes.
flat upper surface.
Okay, okay.
And the trailing edge will be highly cambered. Need
Yes.
not be reflex. Okay, but it will the camber. There will be a trailing edge camber.
Okay, yes, sir.
Okay,
That is why it has maximum camber at 83% of the cards.
Yeah, that is right. No, but this is how it will look like. All supercritical airfoil tend to look like this.
Yes, sir.
Now, after the class, I mean, after
Yes, sir.
I think I should give a small. I will check whether how much you know about supercritical airfoil. It's good to know.
Yes,
Because it's gate portion. So probably, I will check the whole class, not you, me, not you.
sir. Yes, sir.
I will ask the class whether they know about supercritical airfoils, how much they know about it. Okay, or transonic flow.
Yes, sir.
Okay.
Yes. Yes, sir. Then we calculated leading edge sweep angle using this formula. We after calculating, we got 27.
Where did you get this formula from?
Sir, this one from one paper, sir. I
Which
didn't
paper?
cite it. Yes, sir.
That
Sorry,
is,
sir.
you have to cite it.
Sorry, sir. Then from that leading a sweep angle, we calculated the quarter chord sweep angle at maximum thickness. Then taper ratio we calculated. Then root
So
chord.
MAC is in what unit will it be?
It's a meter, sir.
You have to.
Yes, sir. Yes. Then the 3D lift coefficient were calculated as from this formula. Angle at maximum thickness, as I mentioned before.
Again, see, we have the data, 2D data for airfoil.
Yes, sir.
So take the slope instead of 2 pi. Take that slope.
We didn't take 2 pi, sir. We took slope from.
What is that value?
Sir, 5.5548, sir.
CL by d alpha. That is the small CL. Okay.
Yes, sir.
When you write the formula like that, don't like 2 pi. Type it out.
Okay, sir. Okay. Yes.
Okay.
Yes, sir. Then this is our graph, sir. Red one is 2D and blue one is 3D, sir. 3D. Yes, sir. Then base drag estimation, sir. We can. Yes, sir. Hello, sir.
Okay, yeah, understood. Next.
We had high wing because we are doing STL, sir.
Okay.
Yes.
Why STL should have high wing?
Sir, because the engine part should be safe, sir. While
for other, it will not be safe for other.
Sir, no, sir. Then also, sir.
Shouldn't it be safe for all designs?
Sir, yes, sir. But this lift will be high, sir. CL will be more, sir.
If you place the engine and high wing, how will it be more?
Sir, sir.
Just CL depend on the placement of the wing.
So CL does not depend on the placement of the wing, sir. But because of that, we'll land at while landing, our CL will be about 8, sir.
Okay.
So we have a low wing or mid wing. Our engine.
Engine. Tell me, CL 8 means how does it affect the engine? What you're telling is not wrong, but you should know the reason, correct reason for it.
Yes, sir. Sir, I don't.
At very high CL, what will be the angle of attack? Very high angle of attack.
Sir, I have to calculate, sir. I think.
Generally, high CL, you expect high angle of attack, right?
Yes, sir. High angle of attack, yes, sir.
So give me a
low
clue.
speed and high angle of attack.
So what will happen? Will the engine hit the ground sometime?
Yes, sir. That's what I was trying to say, sir.
Why the engine only? The tail will hit first.
Tail will hit first, then engine also will be. Yes, sir.
Then how do you take care of in VTOL or
Yes, sir.
VTOL? Do you bother about the angle of attack?
Sir, no, sir.
Now you have a contradiction.
Yes, sir.
So will the engine tilt in VTOL?
Sir, no, sir.
No?
Sir.
Engine. How do you get vertical thrust?
Sir, engine. Yes, sir. Engine will tilt 90-degree tilt will be there, sir.
Yes. If the engine does not tilt, you can even tilt the nozzle.
Yes, sir. Thrust vector.
So you find out how you are going to achieve that thrust.
Okay, sir. Yes, sir.
That should give you some clue.
So we have to include afterburner also, no, sir? Yes, sir. Okay. Then CD not calculated is this value, sir. Then drag estimation we calculated around 0.0158 calculated value.
Will you
and
calculate
this is,
in Newton?
Sir, no, sir.
Calculate the drag in Newton. You have
sir,
to.
No, sir. I'll calculate. No, sir.
Yeah, you'll calculate. No. Later you
Yes,
calculate.
sir.
What is your density at that height?
Sir, 0.314, sir. 0.314.
Okay, so half rho v squared is CD.
Half Q is equal to 8694, sir.
That is okay. Find out the drag. That is more important.
Yes, sir. Yes, sir. This is our wing platform, sir. Yes, sir. Our CL versus CD graph from -2 to 10 degrees, sir.
What is CL versus alpha graph?
Sir,
yes, sir. CL versus alpha graph.
Sir, sorry, CL versus alpha, CL versus CD graph, sir. Sorry. CM versus alpha, and CL by CD versus alpha graph. Then as you asked us to show the airfoil from the wing platform, I mentioned this image also.
Okay, good.
Yes, sir. So that's also. And these are the references.
You have to know how to cite the references there.
Yes, sir. Third, only that paper one alone I didn't cite, sir. Yes, sir. Thank you, sir.
Thank you. Any questions, Nanda Kumar? Any questions, Nanda Kumar? No? Okay, there are no more questions. Let me. Yes, please, if anyone knows about, first of all, Rajesh, you had a doubt. Yeah.
Yes, sir. So
Uh,
you said that that it's not reliable to use that data to find out the region of stall, right?
mm.
Then how do we know till what range we can actually consider? So how will I know if my airfoil has a huge stall range or not?
You generally assume it over predicts stall by 2 degrees.
Okay.
X file over predicts stall. But then that is why X file has its range of application. Range of it has a limitation, but you want results quickly. Okay. Many a times in design you can't run simulations for a very long time. You get a first idea. Okay, you run X file and see whether how it looks like. I mean whether it is feasible or not feasible. We also have a turbulence model, interestingly, but a very simplified turbulence model. E power n turbulence model is called. Okay, that is account for some turbulence model. As you know, ironically, this is one of the places where the simple model sometimes agrees better with experimental results than a complicated CFT model with turbulence everything. Well, I can't explain these things.
Okay.
Right now, it is beyond human comprehension, but then in future, probably we'll know why.
Okay. Thank you, sir.
Yeah. Yes, supercritical airfoils. Surya Prasad, how much do you know about supercritical airfoils? Has anyone, I mean, have you encountered this in your course somewhere? During a coursework?
No, sir.
Huh? Not yet. Okay. Okay. So, just to give you some idea, okay, shall I share my screen?
Yes, sir. Sure.
Because this is a part of your actually, gate portion, may not be there in your syllabus. That kind of thing. So, the right forum to learn it is aero design. So the supercritical airfoil usually, looks like this. Just to give you a, as you have seen already, it is like this. I'm drawing a very flat upper surface, very rounded nose. Okay. And what is the need for supercritical airfoil? Okay. Um, can anyone, Arantha Krishnan, can I explain?
Sir, I think it's related to like delaying the wave drag.
Delaying the wave drag. Yes, 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 yes.
Uh,
Yes, correct. So,
yes, sir.
does it reduce the critical Mach number?
Sir?
Does it decrease the critical Mach number in any way?
Mm, sir, I think critical Mach number it will be on like later part of the airfoil.
No, no, no. What will happen is
Okay, sir.
there are two Mach. Let's get two things clear. Hmm?
Okay,
Let
sir.
me rub off this. Now, yeah. First of all, you have wing sweep, correct? Wing
Yes,
sweep
sir.
is there, leading edge sweep, right? So if you have a Mach number M here, what matters is for critical Mach number is the Mach number component normal to the wing. This is the normal direction to the wing, correct? There are two components for this M. One is normal to wing. I'll call this Mn. Another is tangential, which is Mt. And this angle is your sweep angle actually. So Mn will be m into cos of this leading edge sweep angle. Okay. So in case without the sweep, okay, you have a straight wing, and you have an airfoil whose critical Mach number is 0.6. That is, if you reach 0.6, if free stream is 0.6, m infinity is 0.6, then somewhere on the airfoil, Mach number will be 1, just equal to 1. Then it becomes less than 1 immediately. Somewhere in the place. So that is 0.6. Now, if you give a sweep, what happens is, instead of m infinity is 0.6, mn is 0.6 is what is take. Okay. So which means that your critical Mach number is now, even if m infinity is 0.6 by cos lambda, your m infinity can be increased. Okay. Sorry, I want to just say this is cos okay. So the m infinity is can be increased to, so up to this Mach number there won't be any Mach number will not reach 1 on the airfoil, like in the normal section, the normal one. So your shock formation will be delayed. Only if it is going more than 1, you will have a shock formation. Okay, we'll continue next class on this. Remind me. After that, I will go to the tail. Then after that, the fuselage presentation. Okay. So, I'll take attendance now.